Okay, another day of flipping the classroom. So this is 2.1 continued. And this first paragraph here, you've now arrived at a crucial point in the study of calculus. The limit used to define the slope of the tangent line, the limit process that we were using today in class, limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. That limit is also used to define one of the two fundamental operations of calculus, differentiation, or in other words, a derivative. So the definition of the derivative of a function should look super similar and familiar. So let's go ahead and write this down in our notebooks, the definition of the derivative of a function. The derivative of f at x, this is the symbol, or a symbol for derivative. It's like f prime of x, so it's the symbol there, is equal to the limit as delta x approaches 0. That sounds like yesterday. Of f of, they've got x plus delta x. Yesterday we had f of c plus delta x minus f of c. And remember, c was just an x value. So now they're dropping the c and they're just calling it f of x plus delta x minus f of x all over delta x. So the derivative is this, provided the limit exists. For all x for which this limit exists, f prime is a function of x. So if with c's in place of the x's, this was the slope, that kind of lets us know that the derivative is the same thing as the slope of the tangent line. So if you find the slope of the tangent line, you're actually finding the derivative. If you find the derivative, that's the equation for the slope of the tangent line. So they're sort of interchangeable. Down here, we should write this down. The derivative can also be used to determine the instantaneous rate of change. Sometimes they simply say the rate of change of one variable with respect to another. So we should write that down. And you've done rate of change before. You did rate of change in Algebra 1. I don't know if you all called it rate of change in Algebra 2 or not, but rate of change was just another application for slope. So they would give you an XY table, and they would tell you to find the rate of change. And all you did was you found, I think when you did rate of change, you said like, oh, we're minusing 1, we're minusing 1. And here we're minusing 2. So it was 1/2, but it was the same thing as slope. So if you didn't remember it, let's just write down. The derivative can be used to find slope, and the derivative can be used to find the rate of change. So rate of change has a lot of broad applications, like speed. That's the change in distance over the change in time, like miles per hour. That's an application of rate of change. How fast the rate that a water tank is filling up, that's the number of gallons going into the water tank per minute or per time, per hour. So there's lots of different applications for rate of change. And this is just wording. The process of finding a derivative is called differentiation. So back up here, when they said, oh, you've gotten to this important part of calculus, one of the fundamental operations is differentiation. So we talked when school began that calculus was made up of 3 ideas: limit, We would use it to help us to find a derivative. And finding a derivative is doing differentiation. And then finding an integral, which is after Christmas. And that's called integration. A function's differentiable when its derivative exists. And it's differentiable on an open interval when it's differentiable at every point in the interval. So let's see here. First off, what do I want you to start writing? So there's different symbols for derivatives. F prime of x, you might see. If you watch that video of the man teaching the difference quotient with the limit, he was talking about little dy and little dx. So that's another symbol or way we can write a derivative. This is the derivative of y with respect to x. Another way we might write it is just y prime. You won't see this quite as often, but, well, you will see this quite a bit actually. The derivative of the function with respect to x. I don't see this one as often, but maybe if we had a different textbook. And maybe they use this symbolism more in Calculus 2, because they talk a lot about differentials. I don't know, it's been a long time since I've done that. But these are just some different symbols that we would use for a derivative. We use this one and this one and this one a lot. And we use this one a lot in when we're writing down derivative rules. In fact, if you looked at that sign that's hanging behind my door in the classroom, I'm using that notation. And I'm afraid that one doesn't come up hardly any. This, we just say dy dx for that. And you can also say the derivative of y with respect to x, but we would also just read dy dx when we read that. We don't say dy over dx or dy divided by dx. We would just say dy dx. Okay, so we don't really know a whole lot about a derivative yet, but we know a derivative of a function is the same as the slope of a function. Sometimes we take a derivative and we are actually talking about slope, and sometimes we're just practicing the process of taking a derivative, and we don't really want to apply it to the slope at all. So example 3, find the derivative of f of x equals x cubed plus 2x by using the definition of derivative. All right, so I'm sort of out of room. I'm going to continue this on the next page. Make sure I put x cubed plus 2x. All right, so if they want us to find the derivative is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. The only thing different about this from what we did the other day is we're calling these x's, we're not calling them c's. We're just calling them x's. So we're going to still follow the rules and follow the steps that the definition is telling us to follow. So the limit as delta x approaches 0. This is the first part we want to do. So you're going to take this x plus delta x and you're going to plug it in for every x here. So you have x plus delta x to the third plus 2 times x plus delta x. So this is something cubed plus 2 times that something cubed plus 2 times that something, minus, this is nicer, all you have to do is rewrite f of x. You don't have to change it at all. We're minusing that whole f of x function, so just parenthesis x cubed plus 2x. You just rewrite f of x right there. So this is super nice. All over delta x. Last year was so long ago. Did we do Pascal's triangle? And did we use it in order to expand a cube? I hope we did. I don't know if we did. If we didn't, please, 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 please ask me about it tomorrow, because it can make our life so much easier. I'm going to go ahead and do it. And if you don't know it, you have to write this down 3 times and do a lot of multiplying. But if you do know it, then it's just 1, 3, 3, 1. We take the first term and it starts at the highest power. I need more room. I need more room. Take the first term and it starts as a cube and goes down. X to the first, x to the 0, which we won't write. And then you take your second term and it starts at x to the 0, which I won't write. And then it gets delta x to the first, delta x to the second, and delta x to the third. And then we do addition between them. All right, so that's cubing it. Now we need to distribute with a 2. I'm out of room. I've got to continue on this next line, but now we're going to distribute the negative here. This is terrible. I'm going to just stick it down here. Minus x to the third minus 2x all over delta x. Now, just like before, nice things should happen and things should subtract out for zeros. You got a positive x to the third and a negative x to the third. You got a positive 2x and a minus 2x. That's it. So we got the limit as delta x approaches 0 of 3x squared delta x plus 3x delta x squared plus delta x to the third plus 2 delta x all over delta x. And aren't we just so very happy that every term has a delta x in it? So we are able to mark a delta x out of everybody. I'm just going to mark through these powers. So that leaves the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared plus 2. And now we're able to take the limit. We're able to plug 0 in for all these delta x's. So 3x squared is not changed, but 3x times 0 plus 0 squared plus 2. So then the derivative is 3x squared plus 2. Because at the very beginning, which I've erased it, but at the very beginning we started out, the first derivative of x equals the limit as delta x approaches 0. So this is our derivative. Now we're not applying it to slope, but if we had a point and we wanted the slope of the tangent line at this point, we would plug in that c value right there. And we'd get 1648, we'd get 50 for our slope. But we're not dealing with slope, we just want the derivative. Okie dokie. we can use the derivative to find the slope at a given point, like I just said. So example 4, if you just wanted to look through it. Actually, we should run through it together. Please remind me to do example 4 with you in class Tuesday. Please remind me. And maybe example 5 also. Be good to go through those together. Example 4 has a square root and example 5 is a rational function. So those would be great for us to do when we're face to face with each other. Let's go on to page 101. We're going to talk about the alternate form of the derivative. Alternative limit form of the derivative. All right, it's useful if we want to think about the relationship between differentiability which means, can I take the derivative? And continuity, which means it's continuous, doesn't have any asymptotes or any holes. All right, so then we could use this alternative form of the derivative, which is f prime of c equals the limit as x approaches c of f of x minus f of c all over x minus c. You really see slope here, because if you think about points written with function notation, a point like x comma f of x, and the other point being c f of c, then isn't this like y2 minus y1 over x2 minus x1? This is slope formula just sitting there. So that is just one way that it really drives home the fact that the derivative is an application of slope. They are equal to each other. All right. So since they're doing the limit here, then that means the limit from the left has to be the same as the limit from the right. So therefore, the limit as x approaches c from the left of this equation must be the same as the limit as x approaches c from the right of that equation. You have to get the same value when you go from the left and the right. If so, then we can do its derivative. So we're going to do example 6 together. The function f of x equals the absolute value x minus 2 is continuous at x equals 2. However, the one-sided limits are not the same. So this is kind of a teaching example. So let's use the alternate form of the derivative. Limit as x approaches c of f of x minus f of c all over x minus c And right here is our c. So c is 2. So this is the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. So they say it's continuous. We know absolute value functions are continuous. This is a v scooted 2 to the right. So that's our graph, and it's continuous. But they say the one-sided limits are not the same. So if we do the limit as x approaches 2 from the left, then we would, absolute value is a piecewise function. So this f of x has 2 pieces. Since it's an absolute value graph, it's equal to x minus 2 let's leave it in bars. If x is greater than or equal to 0, and it's equal to the opposite of it, if x is less than 0. That's why we've got this negative slope when x is less than, I'm sorry, not 0, 2, because we were shifted. And then for the greater than 2, we've got the positive slope. So greater than 2, we've got the positive of the absolute value. And less than 2, we've got the negative of that expression. Oh, whoops. So it's a piecewise function. So if you're going to plug in a value less than 2, you've got to use 2 from the left. You've got to use this less than form of it. So you've got to do the negative of x minus 2. So we're going to be using this part into our alternate form. So f of x would be negative parenthesis x minus 2 minus f of 2 would be plugging that 0 in there, plugging that 2 in there. All over x minus 2. So that would be the limit as x approaches 2 from the left of negative x plus 2 minus, let's see, 2 minus 2 is 0. The negative out front, it's still 0, so minusing 0. These are exactly opposite of each other, and if we factored a negative out, we'd get x minus 2. So this is actually equal to a negative 1. If we did the same process for the right-sided limit, I'm going to do it over here. Then that's x is greater than 2, so we're going to be using this expression. So it's f of x, which is x minus 2, minus f of c, so we plug a 2 in there, all over x minus c. 2 from the right. That's x minus 2 minus 0 over x minus 2. X minus 2 over x minus 2 is just a 1. So the left side, the one-sided limits are not the same. So if you get a different value from the left and from the right, the limit doesn't exist. So since the limit doesn't exist, it's not differentiable. Since the limit as x approaches 2 from the left is not equal to the limit as x approaches 2 from the right, the limit as x approaches 2 does not exist. Therefore, f of x is not differentiable. Well, absolute value is a little difficult to look at anyways. This is enough to give you a headache thinking about this piecewise function involved with absolute value. You don't have to recreate that. What we really needed to see was that if you have a graph with a sharp turn like an absolute value, you can't take its derivative. So let's write down 3 times when we can't find a derivative. One is when the graph has a sharp turn. At C. At the particular x value that we're looking at, that's where the sharp turn happens. 2, the graph has a vertical tangent line. At C. Vertical tangent line, like if we looked at this function, if this is C right here, I've got a vertical tangent line right there. So I can't take its derivative or find its derivative if C is that point right there. And 3, if the graph is not continuous at C. These are reasons when you can't take the derivative. So continuity and differentiability are very closely related. Last thing, just to wrap this part up, if a function is differentiable, at x equals C, then it is continuous. At x equals C. So they say, so differentiability implies continuity. So if they say, oh, we can take the derivative, then we know that it's continuous. However, a function can be continuous and not differentiable at x equals C. So continuity does not imply differentiability. So it's not a vice versa situation. Just think about to the sharp turn, the absolute value. It's continuous, but we learned we can't take the derivative at that sharp turn point. So just because it's continuous doesn't mean I can take its derivative. But if I can take its derivative, then I know it was continuous. Okay, so your job for me is to come in and we're going to briefly touch on these things, and you're going to ask me questions that might have been confusing during this video. So I'm sure there are some. And then we'll just practice problems. We're going to flip to the classroom tomorrow.